All right, you know what time it is? Time for some experimental physics. So we're going to look at how we can determine the spring constant of a spring. So I want you to think about it. Think about how you can do that. Press pause, look through your notes, think about what we've done recently. Come back and we'll look at it, of course. But yeah, think about it. How would you do that? Well, hopefully you recalled, if you're an active learner here, hopefully you thought about the fact that you've seen two relationships that involve the spring constant value. The first one we saw was Hooke's law, right? So you apply a force on a spring, it'll stretch it or compress it by a certain distance. And the stretch distance is proportional to the amount of force. And that proportionality constant is the spring constant we're looking at. The other relationship that we looked at afterwards was we looked at simple harmonic motion and found out that it's got this kind of a cool equation that you can actually measure the frequency. Oh, well, there's a relationship, anyways, between the frequency, the spring constant, and the mass that's bouncing up and down on a spring. All right. So, with those two things in mind, you have an idea of how you could do this. I think it's pretty obvious at that point, I hope. Method one, based on Hooke's law, collect a bunch of data, right? A bunch of numbers for stretch and corresponding force, or force and corresponding stretch, or whatever. We're going to want to have this be I'll move that for now, but I mean, we want to have the force as our dependent variable, which is kind of weird because you'd think of it more so as how much it stretches depends on how much force you put on it. But for convenience to have the equation nice, the k value is going to be based in this equation, so with no fractions. And this is the way it needs to be. So yeah, graph it that way. Hopefully you get a nice straight line. And then what else? And what do you do with that, right? Well, you're going to measure a bunch of distance values, right? So you're going to graph it and so on. Here are a bunch of force and distance values. I'll show you that actually right now, how you're going to do that. I was contemplating getting everybody just to get springs and whatnot from their schools, but I don't really think that's necessarily going to be possible to do. And the force sensor you'd have wouldn't be as awesome as the one I have. So I made a video. So here's the video. Let me just get rid of the sound here because I'm talking instead of the video. But long story short, this video shows a bunch of force values and displacement values. So the video explains it, but I mean, the cart starts at, if I zoom in here, the cart starts at the 20 centimeter mark. So think of that as 0. And then when the cart moves to there, that's 1 centimeter. When the cart moves to there, that's 2 centimeters. There's going to be corresponding force values along the way. So this hasn't started yet. I'm still yapping in the video explaining things, kind of like I'm doing right now. But anyways, there's 20, right? There's the starting point. So there's 1, 2, 3. There's about 4 centimeters, maybe like 3.9 centimeters. You can pause the video wherever you want, and you'll have a corresponding pair of force. This is a force sensor in this cart that's remotely Bluetooth reading to this app in this iPad. Pretty awesome equipment. Anyway, so it's measuring force nice and accurately for a bunch of different locations, right? So that is how you collect the data for that one. And so obviously, if you get that straight line, that's A, confirming Hooke's law. But then, of course, also I need to smartboard going here. I was going to show, maybe I'll just try and do it this way. On here. You're going to measure the slope. I was just going to draw on the smartboard, but I can do it this way. So you're going to get slope. Slope equals rise over run. In this case, of course, slope equals rise over run is really the spring constant value, right? So slope equals, and smartboard's running now, so I may as well just write here, slope equals rise over run, right? And that is your k value. So that's not crazy hard to do. And the other way, based on that frequency stuff, we know that we can measure frequency of a simple harmonic motion, and use the equation that we know to do with frequency and spring constant and mass and so on, right? So those things are known values, and so you can solve for the k value. That video looks like this. So that video, I already had it open somewhere, but here we go. So I show you the mass, so 96.4 grams, so 0.964 kilograms. 0.096? Yeah. Anyways, convert to kilograms. And yeah, so here's the motion, right? And you're going to time that to be able to measure the frequency. Now, for those of you that may not have seen that stuff in grade 11, here's a little refresher, or a little first time ever seeing it refresher for the people that have seen it, I suppose. But when you're measuring frequency, it's not that big a deal. It's just number of cycles divided by the time. The biggest trick is just to be able to identify how many cycles there are in a certain amount of time, or how to count out a certain number of cycles. So let's say, well, I'm going to point out here that a complete cycle is probably easiest to think of it as going like from the top all the way to the bottom and then back to the top, right? So you'd have a cycle, really the spring kind of hangs at a certain spot, right? And you pull it down and then it bounces and goes all the way to the top, and then, and so on. This is the simple harmonic motion, right? But you don't have to start at the middle. And actually, I was saying, pull it down, right? And then let it go. So this is a full cycle, like an upside down sine curve, I guess, right? I just went a little bit too far with my red there. So kind of an upside down sine curve, a full cycle. So if I had lifted it first, then it would have been a sine curve. Anyways, but yeah, obviously a full cycle. But the easier way is just to think of it as, starting at the top and going all the way down and all the way back up is probably the easiest to sort of see on the fly when you're doing your lab. So just to make this a little bit nicer, I'll separate that out, right? So whatever. And sometimes I try to make stuff look nicer. Probably not at this point. All right, so that is going to look like this. All right, help out here because I know it's something some of you might not have done. So we're going to have a stopwatch, and we're going to have the video going somewhere here. All right, so I've got that. This guy, I'm going to do this. Have them both at the same time here. So this one, I want to see the other one. Oh my goodness, I had this all mapped out, but messing myself up. All right, here we go. Make this a little bit bigger. Clicking all over the place here, and it's messing me up. Jeez. I apologize for the awkwardness here. Okay. Here we go. So with this thing bouncing along here, be able to, oh, this is brutal. Let me pause for a sec here and figure this out. All right, I think I got it figured out. That was way harder than it should have been, but got it worked out here. All right, so press play here. This thing's bobbing up and down, right? So I'm gonna look at it and be like, okay, there it is at the top, right? So it's like start, and there's 1, 2, 3, 4, 5. Like for example, that's 5 cycles in 5.43 seconds, right? So the frequency calculation would be wherever here, the 5 cycles divided by that time. Okay, that's going to be a frequency value. And then the other thing I need to show that hopefully you've seen before, but the error analysis part of this. Okay, so when you're writing this up, it's not a big formal lab report. I just need you to do the work, collect the data, make data tables and graphs as needed to analyze things, right? So, and then calculations to get the values. And you're going to get 2 different values for the K value for the same spring. Hopefully they're pretty close, right? Well, how do we compare these values? We need to do an error analysis, right? So more specifically here, a percent error analysis. So for comparing 2 experimental values, you want to look at the difference between the 2. You don't care which one's bigger, so that's why this is an absolute value, right? I always do it as the number experiment 2 take away experiment 1. So we're used to the idea of second takeaway or final takeaway initial or second takeaway first as your change in anything. But yeah, so then divide that by the average of those and you get your percent difference. And the other type of error analysis doesn't apply to this activity as much, but is percent error, so how different it is from an accepted value. So experimental result, take away accepted value, doesn't matter which one's bigger because absolute value, and divide by that accepted value. Oh, and I forgot to add in on this, times 100, stick a percent sign on it. Making this just now, and forgot to add that part, right? So once you've done that, you get like a decimal number. And of course, you multiply it by 100 and stick a percent sign on it. And you've got your percent error. So you'd say something like, oh, these two values are fairly close to each other with a difference of only 2.3% or something like that, hopefully, right? So that is our task. So you've got the videos for data collection, and yeah, and then you just have to analyze and have a chance to see how this works. So I haven't ran the numbers yet. I'm hoping they're pretty close. So we'll see how it goes. All right, cool. As always, thanks for watching.